In this video, I am going to introduce lookup tables by discussing what it is and how it works. After the short discussion, we'll be working through code that displays the numbers 0 through 9 on a 7-segment display using a lookup table. Lookup tables exploit the fact that when you write a value to the program counter, you change the flow of the program. Lookup tables are two-dimensional data tables used to retrieve values from a table of constants using an index value. The offset for which value to retrieve is created by adding a value to the program counter and thus jumping to a specific line in the lookup table and returning with a literal value. In the example, the value of counter is the value that must be converted using the lookup table. The value of counter is loaded into the working register before calling the lookup table. In the lookup table subroutine, the value of W, which is now the same value as the value of counter, is added to the program counter. This creates an offset which is the same size as the value of the variable counter. The return literal in W instruction now executes, loading the literal value into W and returning to where the call originated from. The value in W, which is now the converted value, will now be used. Let us now see how this works in PIC Sim IDE. To save some time, I have already created a program that will count from 0 through to 9 on a common cathode 7-segment display. Before going through the code, let's just simulate this and see what happens. In order to simulate this code, we need to go to Tools, Assemble and Load, and we also need a 7-segment display. So go to Tools, go to 7-segment display, open up the setup and ensure that everything is connected to port B, or that all the pins are connected to port B. We can now go to Rate, select Fast, and we can then go to Simulation and we can click on Start. And as you can see over here on the 7-segment display, we have the sequence counting from 0 through 9. To stop the simulation, just go to Simulation, click on Stop, and the simulation will stop. So how does this work? Let's have a look at the code. The code starts off with two variables that are equated to two different registers. The first one is counter, which we equate to register 20 hex, and the second one is count, which we equate to register 21 hex. Counter will hold the current digit value that is displayed on the 7-segment, and count is the number of digits that will be in the sequence. We have org0, go to initialize, and we have org4, return from interrupt. org0 will put the go to initialize code at the reset vector, and org4 will put the return from interrupt code at the interrupt vector. Below this, we have the lookup table, and as you remember from the short introduction, we have move F, which will take the value of counter and move that into the working register. Over here at add WF, it is added to the program counter, which then creates the offset and will return with a specific binary data byte that will be displayed on the 7-segment display. In the initialization routine, we have bit set file, status, RP0, which moves to bank 1. We have clear file trace B, which will set all the bits on port B to outputs, and with bit clear file status, RP0, we go back to bank 0. The next two lines of code will take a digital value of 10 and move that into count. This 10 is the number of digits that will be displayed in the sequence. In the main routine, we have clear file counter. We want what is displayed on the 7-segment to be cleared. We then call the lookup table. The value that is returned from the lookup table is moved to port B. The value of counter is incremented and the answer saved back into the file. We now move the value of count into the working register and subtract counter from count to determine if we've reached the 10th digit. If we have reached the 10th digit, the 0 flag will be set, and we test for the 0 flag being set with bit test file skip if set. If it is 0, we will go to the main loop and our sequence will start from scratch. If it is not 0 yet, then we will just stay in this loop, displaying the next number in sequence until we reach the 10th one, and we will then start this whole process over again. Let us see how this works when we do a step-by-step simulation of the program. In order to do a step-by-step simulation, we can just go back and say Tools, Assemble and Load to ensure that the code is loaded into the simulator. We then need to go to Tools and we need to open up the Breakpoint Manager. The Breakpoint Manager will ask us whether we want to load the specific code, and we say yes. Go to Tools, go to Rate, change the rate of simulation to step by step because we want to now step through the code. Go to Simulation and click on Start. The arrow points to the starting position, which in this case is the reset vector, which starts at location 0, 0. Every time that we press the F2 button, this arrow will move to the next command that needs to be executed. If we look at this command, it says go to initialize, so after we press F2, it should go to the initialization routine. Before pressing F2, however, make sure that you've highlighted the Breakpoints Manager window. After pressing F2, you will see that it did indeed jump to the initialization routine over here, and the command that will now be executed is bitset file status, rp0. This command will let us move to bank 1 so that we can set up port B as all outputs. Pressing F2 will go to the next command, which is clear file, so the whole of address B will be cleared. We execute the bit clear file command, which in this case will move us back to bank 0. We move the value 10 into the working register. You can see it over here, 0A, that's the hex equivalent of 10. And this command here will move it into the count location, the count register, which is at location 21. And over there you can see that that is now 0A. The next command will clear the counter register. The counter register is equated to register 20 hex. In this instance, nothing will happen. So after pressing F2, you will see that there's no change in that specific register. This instruction will call the lookup table. Let's see what happens. Pressing F2, the pointer jumps to the starting instruction in the lookup table. And this starting instruction is move F. So what we do is we take the value of counter, which in this case is 0, and we move that into the working register. Nothing changed because 0 was just moved into the working register. The working register was 0 to start with. The next command now takes whatever is in the working register and adds that to the program counter. So we are now going to add 0 to the program counter, which means that the very next line will just be executed. Pressing F2 indeed shows us that. After executing the return literal in W command, this binary value will be returned in the working register. Let's see if that happens. So we execute this command. Remember, after executing this command, not only will this value be loaded into the working register, but we should also go back to the command right after the call that called the lookup table. And that's indeed what happens. Remember, in line 17, the call instruction called the lookup table, and we are now ready to execute at program location 18. But look at the W register. There you can see that the value that we had right next to the return literal with W is now loaded into the working register. You just maybe move this down a bit. You can see there it is. So this value over here, binary 00111111, is the value that is now in the working register. Command 18 moves whatever is in the working register to port B. So this data that we have in the working register is now going to be moved to the pins on port B. Let's see what happens. After that movement, a 0 is displayed on the 7th segment because the value that we have here, binary 00111111, is the code necessary to switch on the LEDs to show a 0 on the 7th segment display. In line 19, we will now increment the file counter, and you should see location 20 change to 1. Line 1A will move the value count into the working register, so we will move the value 10 decimal into the W register. You can see that happened there. And now we are going to subtract W from F. So we are going to subtract the value 10 from file counter. So we are essentially going to have a calculation where we take 1 minus 10. The answer to that calculation is not 0. And you will see here that the 0 flag is not set. Because the 0 flag is not set, this test will be false, and we will go back to the loop. Now, let's have a look at the values of count and the values of counter. So the values of counter is equal to 1, and the value of count is still 10. Remember, count indicates how many digits will be in the sequence, and counter indicates which digit we are currently at. If we now call lookup table, the program will once again jump. The value of counter, which is now 1, will be loaded into the working register. There it is, we can see it over there. Whatever is in the working register will be added to the program counter. Look at the value of the program counter. The value of the program counter currently is 6. So if we add 1 to the program counter, then the program counter will jump to location 8. It's 8 because the next instruction will be 7, but we are adding 1 to the 7, therefore we get 8. We are going to return with 00000110, which is the 7-segment equivalent of a 1. Pressing F2, you'll see we've loaded that into the working register. That value is now moved to port B. You can see the 1 being displayed. We are going to increment the file counter. You can see we're now going to display the 3rd digit in the sequence. Remember, we started counting at 0. We're going to move the value count into the working register. So the working register will now become 0A. There you can see that. We're going to subtract W from file counter. So whatever is in the W register is going to be subtracted from whatever is in the counter register. The counter register currently has the value of 2. We're going to take 2 minus 10, and we're going to test that answer for a 0. So we subtract it. We can see here that there is no 0 flag that's been set. So once again, the 0 test will be not true, and we will just continue and jump back to the loop. This process repeats itself until we get to the last digit in the sequence. And I'm going to run this step by step in order for us to get to that point so that I can explain to you what is going to happen when we actually get to the point where this test is true. Okay, so the value in counter is 9. So we're almost finished with this count sequence. Let's see what happens. We call the lookup table. We move the value of counter into W. So the value of W is now 9. We are going to add 9 to the PC. And we get to 10 hex. And we are now at the last line. So we are now almost finished with a sequence. And we're going to load the binary value that's equivalent to 9 on the 7 segment into the working register. There you can see that. We're now going to display that value on port B on the 7 segment. We can see the 9. We're going to increment the file counter. And you will now see that the file counter as well as file count has the same value in them. We load the value count or the value of file count into the working register. And we are now going to subtract the working register from file counter. So we're going to subtract 10 from 10. And when we subtract 10 from 10, we know that the answer is 0, which means that after this subtraction, the 0 flag should be set. And you can see there that the 0 flag is indeed set. Now this test will be true. And instead of going to the loop, we now go to the main routine because this test tested the 0 flag and it skipped the very next line if it is true. Going to the main routine will clear the file counter. You will see that after that command, the file counter will become 0. We will call the lookup table, and this whole process starts from scratch. So 0 will be loaded into the working register, 0 will be added as an offset, and the very first return literal with W will be returned to be displayed on port B. This process now repeats itself until the power is removed, or in this case, until the simulation is stopped.